Welcome to special talk of Department of Mineral Resources or DMR. This is the the third talk of this fiscal year, and it's really a special talk because it is co-hosted by CCOP Technical Secretariat. First of all, may I introduce myself? My name is Pachara Sangan from International Cooperation Section, and I have a great honor to be your Master of Ceremony for this special talk. In this occasion, I would like to invite Mr. Thinakorn Thathong, the Inspector of Department of Mineral Resources, to deliver the welcome address for this special talk. Please.
Thank you very much. Good morning, Dr. Jeong Julie, Director of CCOP Technical Secretariat, and Dr. Adisha Surintham, former Director CCOP Technical Secretariat, Professor Dr. Jeong Kim, Professor the University of Calgary, Canada, DMR Executive, esteemed guests. My name is Thinakorn Thathong. I'm Inspector of DMR. I'm delighted to represent the Department of Mineral Resources under the Ministry of Natural Resources and Environment of Thailand in welcoming Dr. Jeong Julie, Director of CCOP Technical Secretariat, Professor Dr. Jeong Kim from University of Calgary, and all esteemed delegates to DMR for today's special talk. Since 2010, DMR has been hosting a series of special lectures as part of our international cooperation in geology and mineral resources. Annually, we conduct about 10 talks, creating a platform for knowledge sharing, experience exchange, and enhancing skill in both technical aspects and English language proficiency. Esteemed guests, we are privileged today to have Professor Dr. Jeong Kim, an expert in geophysics, present a lecture titled Superconducting Gravimetry for Geohazard Analysis, focuses on earthquake early detection and Geological CO2 storage monitoring. It's very interesting issue at this moment. A special thanks to Dr. Jeong Julie, Director of CCOP Technical Secretariat, for co-hosting this insightful section. In the face of the global climate change and its impact on natural disaster, geoscience has emerged as a crucial field for helping society adapt to a changing environment, live harmoniously with nature, and use nature resources effectively and sustainably. Esteemed guests, I'm again thrilled to welcome Professor Dr. Jeong Kim to the AMR. We are eagerly anticipate learning from Professor Kim, expertise and exploring opportunity to enhance cooperation aimed at sustainable development and improving people's life. I wish everyone a successful and enriching experience in the special talk program that lie ahead. Thank you very much.
Thank you very much, Mr. Thinakorn, for your welcome address. And I would like to invite Dr. Jeong Julie, the Director of CCOP Technical Secretariat, to deliver the remark for the special talk, please.
Sawadee Krap, Sawadee Doncha, good morning. It's my great pleasure, as always, to come to DMR because CCOP is just not just a neighborhood of DMR, but we are like a family. So I'm always very happy to come to here and to meet our family again. This today, actually, as you may know, we have a very special professor from University of Calgary. Actually, Dr. Jeong Kim published the paper in Nature Communication last year on this actually topic, which is really cutting edge and then new methodology to detect big earthquake by using special superconducting gravimeter. So he is very busy. He is invited very special talk with some very famous academic society meetings like AGU or maybe EGU, and then Japanese big meetings for because they are very keen to know the methodology, new methodology of how we could detect or even have some early warning of the big earthquake, which is really very, very good, especially those countries who is located in ring of fires, so can have some time to evacuate and then can save a lot of lives of human, and then also some our big asset. So let me very briefly introduce about Professor Dr. Jeong Kim. Jeong Kim received his bachelor and master degrees in geophysics from Yonsei University in Korea, and got PhD in major in satellite geophysics from School of Earth Sciences at the Ohio State University, Columbus. And his professional career, which includes research scientist at the State University of New York, Albany, and then he was also researcher in NASA in the Planetary Geodynamics Laboratory for a while, and then he was a professorship in Sejong University in Korea, and then finally, and then currently he is a full professor at the Department of Geomatics Engineering at the University of Calgary. So he has been in Canada as a professor more than 17 years is my understanding so far. And then, as I already mentioned, he has a lot of papers, but one of the recent accomplishment of him is he has published a Nature communication paper on this issue. So this is quite new, and then maybe can give you some new information how we could save our lives based on geohazard, and how we can. And then also he will give some more information about by using that gravimeter, how we can tackle the carbon dioxide issue, which is also very important for all of us. Okay, so please enjoy his talk, and then please do not hesitate to ask some question to him. Okay, maybe can we invite?
Okay, thank you. Thank you very much, Dr. Lee, for your warm remarks and introducing Professor for everyone instead of me. Okay. Okay, ladies and gentlemen, please welcome Professor Dr. Jeong Woo Kim to deliver his presentation in this special talk. Professor, please. รอสักครู่นะคะเดี๋ยว
Sorry, I have to say also, I really appreciate the DMR for inviting Jeong Kim and then me to such a nice occasion. Thank you.
Hello. Okay. Good morning, everyone. Can you hear me? Okay, thank you very much for joining my talk today. Thank you, Mr. Tatong and
It's okay.
Then
You can stand.
I will use this. How is it? Okay, okay. Thank you, Mr. Taton and Dr. Lee, for giving a good introduction about me. And I'm honored because this DMR is really a well-known department. Especially important because rare earth elements are kind of focused these days. So I think your role is really important. So today I'm going to talk about the application of superconducting gravity to earthquake early detection and monitoring geological CO2 storage. As far as I know, the Thailand has a target to achieve net zero carbon by 2060. Okay, so Korean government actually set up the goal 10 years earlier, which is 2050. So, and also I know that the Thailand has a big earthquake, particularly in the northern part, Chiang Mai. I know this southern portion of peninsula is stable, but if we go to north and there we can expect a big earthquake. So I wish my talk will play a small role to the earthquake detection and the CO2 storage. So I am not going to give detailed information on very complicated theory principle behind this, but I will try to, I'll do my best to make you understand this complicated topic. So, okay. Okay, so today, first, I'm going to talk about the, oh, it's too bright. Okay, sorry. Okay, so I will give you the brief introduction about the state-of-the-art gravity machine, gravimeter, which is normally 1,000 times more accurate than the typical spring-type gravimeter. And that was actually installed in Korea at one of the deepest astrophysics and geophysics lab in the world. And then I will give you the introduction of the lab, and plus I will then how can I point out? Is it anyway? Is there any other option?
It's LED, so you cannot.
Okay, it's LED. Okay. That's fine then. It's okay. So then after the introduction of the machine and the layout of the lab, I will talk about my past, current, and upcoming research for the earthquake early detection, which will be followed by the microgravity monitoring of geological CO2 storage. Okay. Okay, so in the left-hand side figure, when we have an earthquake, okay, and then the fastest earthquake signal, which we can detect, is direct P wave. Okay, so this is the hypocenter of the earthquake, and then the direct P wave arrives at the seismometer. This is a typical earthquake signal we use for the earthquake early warning. Okay, so as we know that the direct P wave travels about 5 to 8 kilometers per second. Okay, so therefore, when earthquake occurs, then we have to wait until the direct P wave arrives at the seismometer. Okay? So seismometer is the typical machine instrument which is used by the network. Okay, so probably Thailand has a good seismometer network, and then they use the seismometer. Seismometer is also known as accelerometer. Okay, and then the right-hand side figure shows a lot of interesting things because, as I just mentioned, I think it's too wide. That's okay. Okay, and then recently, a French scientist discovered that in addition to the P wave or even S wave, there is a gravity acceleration signal, which is called prompt elastogravity signals, PEGS. This signal travels at the speed of light. In other words, when earthquake occurs, then at the same time of the onset of the earthquake, if we can detect the elastic signal, so I'm going to call it PEGS, then we don't have to wait until the direct P wave arrives. In other words, we can immediately detect the earthquake because the PEGS travels at the speed of light. So I'm going to talk about that, how we can detect PEGS, which travels at the speed of light. So this figure this doesn't work. Okay, good. So this figure shows how fast the PEGS travels. So for example, this green, do you see the green small bar? That is the time when first direct P wave arrived at these seismometer stations for the 2011 Tohoku earthquake. So the red star,
Okay.
this indicates the epicenter of devastating 2011 earthquake. And then this MBJ station, for example, which is about 1,284 kilometers away from this. And then if we use conventional seismometer, then it took 165 seconds until the seismometer located at this MDJ, Mudinjiang station in China. Okay, but if we detect the gravity signal, then we can immediately detect the earthquake at the onset of 2011. Therefore, we can save 165 seconds to save human lives and to protect our the money, for example, right? So this shows everything. So the French scientist discovered that we can detect the PEGS at the onset of the earthquake. Does this work? Oh, good. Okay. Can you see it? Can you see it? Okay. Okay, so this is the basic principle. Okay, if we can detect the PEGS, then we can detect the signal at the same time when earthquake occurred, right? Which means even for the East Asian countries, we can save anything between 100 seconds to nearly 200 seconds, which is a big amount of time in terms of earthquake early warning. Because, for example, in Japan, they want to predict the earthquake as early as 1 second, which is a significant amount of time to slow down the express train Shinkansen. So what they told me was that if they have 1 second, then they can slow down the Shinkansen express train like significantly. So 1 second really matters. But there are two limitations if we want to use PEGS for the earthquake early warning. One limitation is the magnitude of the earthquake. So it is supposed to be 8.9, magnitude 8.5 or greater, which means that this PEGS can be detected only with the earthquake, which is greater than 8.5. So this is the major problem, because small earthquake, we cannot detect PEGS, right? Second limitation is the distance between the epicenter and the sensor. So if it is too close, then we cannot detect it. If it is too far, also we cannot detect. So the optimal distance between the sensor and the source should be between 1,000 and 2,000 kilometers. So in the past 19 years, I have been working with superconducting gravimeter, which is the most accurate and most stable machine. Okay, and then that machine was installed in how can I go to the next slide? Next slide. Okay. I think we maybe next slide. Okay, so 2022 October, I installed my superconducting gravimeter in Korea, right here. Okay, and then this location is great because this sensor is about between 1,000 and 2,000 kilometers from the potential big earthquake source. So here, this cyan star shows the epicenter of Tohoku earthquake, which is about 1,250 kilometers away. And also these yellow stars shows the next upcoming big earthquake estimated by Japanese scientists. So from this figure, this Taiwan, Ryukyu, Nankai, and Tohoku, these are the potential location of the next big earthquake. Therefore, this machine installed in the Korea may be able to detect the big earthquake at the speed of light. Then we can save about 2 minutes for the evacuation of the people, slow down of the train, and so on. So geographically, this location is very meaningful. Next slide, please. Okay, so this is the layout of the underground lab. So Korean government built a underground astrophysics and geophysics lab, which is shown here. So this is a 3D layout. So this is the surface of the Earth, and this is the underground lab. So my machine is installed here, which is about 1,008 meters below the surface. So we have a huge overburden, but the benefit is this is very quiet, environmentally very quiet. So no human, no environmental noises around, so that the quality of the data is optimal and excellent. So I wish this best machine in the quietest place will be able to detect PEGS. Okay, so anyway, so this is really deep, and then this lab was built based on the active iron mine, because Korean government tried to save money, because if we dig from the scratch, then it takes time and money to go all the way down to 1,000 meters, right? But then, fortunately, there is active mining. So the Korean government built this underground lab as an extension of the active mine. So, but still, it took many years, and they spent big money. However, this lab was completed in October 2022, then I immediately install and operate my machine at this point. So this is even below the mean sea level. So this is about 120 meters below the sea level and about 1,000 meters below the surface of the earth. So this is the deepest gravimeter ever installed by human being. And then this is the most quiet environment which we can expect. So this lab was originally designed to detect dark matter. Okay, because we don't expect any noise, but this is also a perfect location for the earthquake early detection. Next slide, please. So whenever I present this, then people want to see how we can predict earthquake. So it is really not a good idea if I mention either precursor of earthquake or predict. What I'm going to say is early detection, okay? Because we still need the rupture of the rock, right? Then I plan to detect the earthquake at the same time because PEGS travels at the speed of light. So I would say, and I have to say, early detection rather than precursor or the predict, okay? So early detection means at the onset of the earthquake, we try to detect, okay? So this is how the lab was constructed. So this is the elevator shaft, which actually leads to the access tunnel. So this is about 1,000 meters below the surface. And this is the tunnel. Then if we move another 900 meters by golf cart, electric golf cart, then we arrive at this space where I constructed 3 concrete villa, which is coupled with the basement so that my gravimeter can be really installed on top of solid rock to feel the vibration sensitively so that we can detect the earthquake. Then this is my machine, okay, installed below 1,000 meters of the surface. So this is cryogenic machine. I will explain this later. So that just like an air conditioner, we need to maintain the sensing unit about 4.0 degree Kelvin, which is really cold, right? To maintain superconducting status. Therefore, this machine is otherwise known as cryogenic machine. Okay, next. Okay, next slide. Okay, then I will show you what the machine looks like. Next slide. Okay, so this figure shows the gravity sensing unit of the superconducting gravimeter. So I'm not going to spend big time, but I have to mention that with this cryogenic machine, there is no mechanical spring to support test mass. So every single gravimeter has a test mass, which is supported by mechanical spring, which means that if the Earth's mass attract the test mass, and then the spring will be extended, right? And for another example, if there is a oil or gas reservoir below this test mass, and then the length of the spring will be shrink. Okay, so if we are able to measure the change of the length of the spring accurately, then if we convert the length of the spring into the acceleration unit, that is the principle of the gravimeter. Okay, but then the problem is with the mechanical spring, because as time goes by, then due to the mechanical creep of the spring, so we have to accept the error from the creep of the spring. Okay, but this one is interesting because our test mass is 1 inch 5 gram niobium sphere, which is shown in gray. And then this is magnetically levitated in cold environment, which means it does not include any mechanical spring to support. Instead, this is magnetically supported from the below. So, you know, you have heard about express train with the magnetic levitation, right? So this is exactly the same. So this is completely, this test mass is completely floated. So there's nothing, no mechanical spring actually holds this. This is the benefit. So there are two coils, upper and lower coils. So this lower coil actually supports from the below, and then this upper coil holds this test mass from side. Okay, so this is the typical concept or principle of the superconducting gravimeter. Next slide, please. Okay, so if we compare the superconducting gravimeter with other conventional gravimeter, this is what it looks like. So, for example, in terms of precision, this superconducting gravimeter is 1,000 times more precise than the conventional gravimeter, which uses the mechanical spring. For the drift, this superconducting gravimeter has this small drift because it doesn't have any spring. And also this drift is linear. Therefore, we can correct it. But conventional spring gravimeter has this big drift, which is nonlinear. Therefore, this is 1,000 times accurate, more accurate, and then extremely quiet. And also, we can monitor or we can observe the gravity data as long as years. Based on my experience, for 5 years, we can continuously monitor the gravity at 1 second sampling interval. So that's why scientists want to spend about $0.7 million to buy this one. So this is about 12 times more expensive than the conventional gravimeter. Next slide, please. Okay, so I'm not going to spend big time, but this graph shows that this blue curve, which is from the Korean machine I installed, shows the lowest noise, particularly in the seismic band. So this shows that the Korean machine is the best in terms of noise. So it is installed in a quiet region because it's deep, right? So that we have a better chance to detect the PEGS. Next slide, please. Okay, so next. So next slide. Okay, so about 18 years ago, when I was in Korea, I installed my first superconducting gravimeter in one of the seismometer station operated by KIGAM, Korea Geoscience Institute of Geoscience and Mineral Resources. So this is the overview of the observatory. And then this is the machine that I installed and operated. And this is observatory type, which means this is a huge machine. So I operated for 3 years. Okay? And after that, I bought the portable superconducting gravimeter, which is called iGrav, IGRAV. And then it has a serial number of 001, which means I was the one who bought this machine, the first in the world. So I still use this machine. And this machine was installed in Canada. Then it was fully refurbished. And then 2022, it was installed in underground lab in Korea. Okay, so this serial number 001 is about 20 years old. However, this was fully refurbished, remodeled, and then installed in Korea 2022. Okay, next slide. Okay, so when this machine was being operated in Korea, we analyzed 4 earthquakes. So this is the location of the old Korean machine at Mungyong, which is about the center of the Korean Peninsula. And then these 4 earthquakes are analyzed so that if there is any meaningful a signal was detected. That was a long time ago. And then the epicenter of these 4 earthquakes are shown in this figure, small figure. So, for example, for earthquake number 1, this is the location, and then that magnitude was 4.8, and then the depth was about 13 kilometers below the surface. So what we found from this study was that this is the onset of the earthquake, and this is the time. Okay? And then what we found was that after the earthquake, there was a permanent gravity change, which is about 0.06 microgauge, which is very small, but there is a permanent change after the earthquake when you compare the level before and then level after earthquake. So this is the permanent change of the absolute gravity, which is significant because absolute gravity is the good standard for the survey or military purposes, right? So this, although this amount is small, but entire national gravity map should be revised. Okay, next slide, please. Okay, then, as I just mentioned, I installed that machine, the different machine, 001, in Cascadia subduction zone in Pacific west coast of Canada, because this area, Pacific Canada, it's tectonically very active zone because the Juan de Fuca plate subducts beneath the North American plate. So I installed my machine at here, right on the top of the sleep zone where we experienced silent earthquake. Because this is very seismically active zone, however, due to the special tectonic setting, we cannot feel the earthquake on the surface. That's why this type of earthquake is called silent earthquake. Silent earthquake means we know there is an earthquake, but that cannot be detected either by machine or people on the surface. Next slide, please. Next slide. Okay, so next slide again. So this is the typical and conventional data processing we have to take care. So I'm not going to explain this, but I just want to show you that this is really a complicated procedure. Next slide. So once we, correct for all the noises and environment, then we ended up with having 2 earthquakes, which shows meaningful result. So my machine is located here, and then the first meaningful earthquake was named Haida Gwaii earthquake with a magnitude of 7.7, and then the epicenter is about 708 kilometers. So similar to the previous result from Korea, so this Haida Gwaii earthquake created about 2.6 microgauge change of gravity permanently after the earthquake. So this earthquake, about 800 kilometers away, still changed the gravity at this point about this much. So this is very significant because this means that there was a mass redistribution below this area by the earthquake. Okay, and then next slide. And then there was another earthquake was followed. So that was Craig, Alaska earthquake. This is the magnitude. And then this was about 1,060 kilometers away. But strangely, this is the similar earthquake, but there is no change whatsoever before and after the earthquake. So we still don't know why. Sometimes some earthquake change the density. Some earthquake does not change the density of this area. So we don't know yet. Okay, so this needs a further investigation. Next slide. Next slide, please. Yeah. Okay, so this is the paper that was published in November 2022 in Nature Communication. So what we found in this paper was that first time ever, we estimated the amount of the gravity change by the movement of the plate, okay? Which means that when the Fuka plate moves from west to east, which means from the Pacific side to the Canadian side, and then it actually compacts the crust, okay? And then when the crust is compacted, then density increases, right? Because it becomes denser, then strain accumulates. Then someday, it needs to release the accumulated strain. That is the earthquake. So what we found was that even though we don't know when earthquake occurs, however, we successfully estimated the increase of the density by the movement of the plane, which actually caused the increase of the strain, which eventually will make megathrust, big earthquake in the area. So this is what we found. So I still mentioned that we can roughly estimate how fast the strain is accumulated. However, unfortunately, we do not know when the big earthquake will happen. Okay, but then this is the good step because we know the subduction rate, which is about 4 or 5 centimeter per year. Then that will increase the density this much, which will increase the strain that much. Then eventually that will be a good indicator of the mega earthquake. Next slide. So I'm going to just skip a few slides, please. Okay, please. One more. Okay, this one. So I just want to explain this. So what we did was, in addition to the gravity data, we analyzed GPS signal, surface GPS signal, to model the horizontal strain and the vertical strain. And then we computed, by using these two, we computed three-dimensional compaction rate of the crust. Then we computed the density change from this. So due to the subduction, so density of this area is increased this much, which eventually can convert it into the strain. So then someday there will be an earthquake, probably around this area. So this is my interpretation of this map. The next slide, please. Next slide. So I just want to skip. Okay, so next slide. Okay, then I'm going to talk about the YEMI-Lab gravimeter, which I installed about a year and a half ago. So let's go. Next slide. Okay, so my machine installed at 1,000 meters below actually detected this many earthquakes between the first 6 months of the operation. So the horizontal axis shows the time in Korean Standard Time, and then the top two blue curve shows the earthquake that were detected by nearby seismometer. And this black curve is the gravity signal that was detected by my gravimeter, which means this detects the direct P wave. Okay, from the first slide, do you remember the direct P wave, right? This is the seismic elastic signal, and this is gravity acceleration, even though they look like the same, but what my machine detected was the change of the gravity. Okay, but both seismometer and gravimeter are considered as accelerometer because they also detect the acceleration of the Earth. But then, as you see here, so my machine also perfectly behaves like the seismometer. Okay, next slide, please. So And then we analyzed 4 earthquakes. And then next slide, please. And then we could not, up to this point, we could not find any significant the gravity change. Okay, and then as I mentioned at the beginning, we need 2 conditions, right? One is the distance between the source and the sensor. And the second one is the magnitude, right? It is very unfortunate because there is no such an earthquake occurred since I installed my machine, right? Yeah, and I shouldn't say that, but you know, I really want to see. I don't want to see it, but there's no such event yet, which is really great. We had a big earthquake, but sometimes that was too far, like Turkey. It's way too far. Or we have a good earthquake in Japan, like December of 2022, but that magnitude was only 4.3. Okay, so none of the earthquake actually meet the requirement, which is fortunate, but scientifically, I mean, it is not very fortunate. But what I want to do is, since our gravity machine is installed in very, very quiet environment, so we may be able to reduce the minimum magnitude of earthquake down to 6, for example, not 8.4. And also the distance limitation. Yeah, I want to see if we are able to detect more PEGs with a wider area. So that's what I am working on. So next slide, please. Next one. Okay, so then from the next 5-6 slides from this is my proposal to Korean government. So what I propose to Korean government is that I want to install another superconducting gravimeter on the top of the current meter, which means these 2 gravimeter, identical gravimeter, will be vertically coupled. Then the benefit of this is 2 things. We can have nice 3-dimensional density models nearby, okay, in the entire area. Plus, when we couple these 2 gravimeter, then we can compute the vertical gradient. For example, this is 10, this is 9, this is separated by about 1 kilometer away. Then we can, we can compute the vertical gradient, right? That's the benefit. Next slide. Next slide, I'm going to skip. Next slide, please. Yeah, so this is, we went to, okay, okay. Okay, so this is the concept. So if we have the vertically coupled gravimeter, then this is exactly the same as the typical gravity gradiometer. Okay, so, and then, okay, so we have, I propose to have one vertically coupled gravimeter, plus I propose to install another 2 vertically coupled gravimeter in other part of Korea. So next slide shows where. So in addition to the Yemi lab, underground lab, Korea has 7 power plant which has an underground facility. For example, in Yangyang, which is located in the eastern coast of Korea, there is already underground lab. It's government facility. So I propose to install 2 gravimeter. They are 7 meter vertically apart. Then we will have second set of 2 gravimeter. The next slide, please. Then eventually we will have 1 set of vertically coupled gravimeter, second set, and then we have real nice mathematically well-designed network. Then we will be able to increase the possibility of detection of PEGs. So my goal is to widen the range of the detection in terms of magnitude, right? If this network works so that we can detect even with the small earthquake, which is great. And also by using horizontally analyze the network data, then we should be able to extend the range of the detection. So currently it should be between 1,000 and 2,000 kilometers away, but I wish we can actually widen the range so that we can detect more earthquake. Okay, so this was the last slide of the earthquake detection. Then this is kind of a proposal to Thailand government. So very recently, our university and the Korean National Institute for Mathematical Sciences actually organizes East Asian Network Initiative for Gravity Measurement, okay, alliances, which means the left-hand slide shows the current location of the superconducting gravimeter. So if we share and then analyze all these 16, 17 data, then we should be able to increase the chance of the detect of the PEGS. But I suggest like countries like Thailand and then Indonesia or Vietnam, they have a national network of seismometer, right? So even though these countries do not have superconducting gravimeter, but if they can join the system through CCOP, then we should be able to have a real nice network of seismometer and the gravimeter, which will dramatically increase the chance of detecting the earthquake. Okay, so I really want these CCOP countries to join the network so that we can cooperate together to protect our human lives and right, and then the asset. Okay, next slide. Then I will shift my focus to the gravity monitoring of geological CO2 storage. We use same machine, superconducting gravimeter, and then about the same skill technique to detect leak or the migration of the injected CO2, which is important because injection of CO2 is not easy because we have to make it the supercritical condition, and then we have to inject the supercritical CO2 into, for example, a saline aquifer, right? About 700-800 below. Then we have to monitor whether or not the injected CO2 plume stays there, or sometimes it leaks to the atmosphere, which is not good, right? So I will be talking about how we can monitor the injected CO2 by using superconducting gravimeter. Okay, next slide, please. Okay, so as I mentioned at the beginning, I know that Thailand has a 2060 carbon neutralization plan, but the Korea has a 2050 goal, right? So I got this from a Korean government, but according to the Korean government, in order to achieve net zero by 2050, Korean government must reduce the CO2 by this amount. Okay, the second last column. Okay. Okay, that's fine. So, which means whatever happens, the geological storage must play an important role to reach the carbon neutralization goal. I'm not sure how Thailand will achieve the goal by 2060, but I believe that the injection of CO2 into the subsurface must play an important role. Otherwise, I don't think Thailand can achieve the goal. I really don't know about that. So anyway, so Korea is heavily dependent on the injection of CO2 into the ground. Okay, and then this is what we need. So by 2050, Korean government need to secure about total of 2 billion ton of CO2 storage, which is really challenging because now the secured the CO2 storage is really minimal. So we have to dramatically find more and more storage to store about 2 billion tons of CO2 underground by 2050. Otherwise, the Korean government goal cannot be achieved. So next slide. So next slide, please. Yeah, the next slide is okay. Yeah, let's skip one slide. Okay, so this map shows the location of the potential CO2 storage. Okay, as you see in this map, Korea must be depend on the offshore side, which means we have to inject the CO2 into the ground in the ocean, so continental shelf. So if you see this, for example, so this is the Yellow Sea. This is the sea between Korea and China. Okay, and this is Japan. This is Japan and this is Korean Peninsula, right? So we have huge the sedimentary basin here, which is called Gunsan Basin. So we plan to inject the CO2 into the sedimentary formation. And also in the eastern part, we have a depleted gas reservoir. So we plan to inject the supercritical CO2 into that area. And then in the southern part, so this is Jeju Island, and they plan to inject the CO2, but not into the sedimentary basin, but into the basaltic layer, which I'm going to explain. So as you see in this map, the blue color shows the confirmed storage, while this green means potential. So in this map, we have only one confirmed storage, which is depleted gas reservoir. So this is the problem because we have only one confirmed storage and all others are kind of potential. So we have to develop a lot of potential storage. Otherwise, carbon neutrality is not easy to be achieved. So next slide. Okay, so now this is very controversial topic because, as I just mentioned, even Korean government is considering injecting CO2 not into the sedimentary basin, but into the basaltic layer. Okay, so can I just go to the next slide? Okay, so because this is easier. So conventional CCS is shown on the left-hand side. So we make the CO2 into supercritical condition. So supercritical condition means it's like a dry ice. It's not liquid, it's not gas. It's something between the gas and the liquid. Then we have to inject that supercritical CO2 into subsurface where we have to have a cap rock to secure it, right? To do this, we need a good permeability and porosity to inject, right? And also it should be supercritical, which means the temperature and pressure condition must be met. So the storage is very, very limited because it should be deep enough and there must be a cap rock on top, and then it should be deep enough to maintain the supercritical condition. So this is why it's not easy to find the potential sedimentary basin to store CO2. However, on the right-hand side, this technique is called carbon capture and mineralization. In this case, it takes about 10,000 years when we expect the injected CO2 becomes mineral, okay? So it takes 10,000 years. So we have to keep monitoring like up to 10,000 years, maybe more, to confirm the injected CO2 became solid. Then it's safe, right? There's no possibility that the injected CO2 leaks to the groundwater aquifer or leaks to the atmosphere, right? But then on the left-hand side, as you see here, we don't have to make the CO2 supercritical, which means we just mix the CO2 with the seawater and then inject into the basaltic layer. So basaltic layer is very porous, okay? And then that is normally ultramafic, which means that ultramafic rock and the injected CO2 react fast, such that as short as 2 years, the injected CO2 becomes mineral, okay? So it's too fast. And also, there are plenty of basaltic layer all around the world. For example, in Iceland, okay, so mid-oceanic ridge, we have bunch of ultramafic rocks, right? So if this technique is possible, then we don't have to worry about the limitation of the storage anymore, okay? So this was actually confirmed at a pilot study, but not either commercially or even I mean, it is confirmed. We know that that technique happens. So can you go back to the previous slide? The previous slide. Yeah. Yeah, go backward, please. Okay, so this is what the slide is about. So conventional method takes 10,000 years. Okay, and then we have very limited storage, but this is confirmed, right? Confirmed technique. However, the CCM, carbon capture and mineralization, we have almost unlimited the reservoir space, which is great for every country. And it takes only 2 years, which is great, but that is dangerous because even during the injection, it could be mineralized. But it was scientifically confirmed, but not accepted yet. So it is challenging, but if this method, CCM, is confirmed possible, then it's a game changer for every country. I don't know, this Thailand has a volcanic plateau. Is there a volcanic rocks in Thailand? So you have a big plateau? Or how about porosity? Is it good? Is it good? And must be mafic or ultramafic, right? Then you also have a potential to use CCM, okay? Once it is internationally accepted, okay? Okay, go to next slide. So this is this could be a game changer if it is possible, okay? So even Korea has the basaltic reservoir as a potential of the storage. Okay? Go to next slide then. Okay, so from this slide, I worked with the Korean government and Canadian government for the monitoring of CO2, injected CO2, because based on my research, only superconducting gravimeter can detect the migration of the injected plume, because it can collect the data for up to 5-10 years continuously, and also its accuracy is barely enough to detect the injected CO2. Okay, so I don't want to explain in detail the manner, but okay, this is okay. So no, you just go. Okay, so this graph shows that the injected CO2 can be monitored on the surface of the Earth with the superconducting gravimeter. And particularly this slide shows that, that as I mentioned, the Korea depends on the offshore ocean storage. Therefore, I simulated that the superconducting gravimeter is installed at ocean bottom, not on the solid Earth, but ocean bottom, because Korean case, it is always offshore, right? So I had a bunch of simulations, and I concluded that we can detect the change of I would say change of mass or migration of the plume even at the bottom of the ocean. Because, for example, Gunsan Basin, that ocean depth is about only 50 meters. 50. It's very shallow. So that I'm going to show you how, but if we install the gravimeter at the ocean bottom, which is about 50 meters below, then we should be able to detect the change of the mass or the migration of the mass by moving the injected CO2. Next slide, please. Okay, so anyway, I did lots of work so that when there is a surface deformation, but we still can monitor the change of the mass, or if there is any volume change or something happen within the reservoir, but still we are able to change the mass of the injected CO2, which is great. Next slide. Okay, the next slide. So, okay, so as I mentioned, for the offshore storage, we cannot detect the change of the CO2 on top of the water. Okay, so we have to install the machine at the ocean bottom. So this is the slide of the slide case. They deployed conventional spring gravimeter twice, one in 2002, one in 2005, and they said they monitor the change of the mass around the injected plumes. I think the CO2 was injected here, but in 3 years they migrated this much. Okay, so this is not enough because what I want is to continuously monitor the data so that the injected CO2 stays there securely. So next slide. So, okay, so this is actually the Korean CO2 platform, and then with the help of the manufacturer of the iGraph, so I proposed to Kigam, actually where the Dr. Lee is permanently affiliated, to design the pressure cage shown here on the right-hand side. So we can contain the superconducting gravimeter in the well-sealed box and then deploy down on the surface of the ocean. So next slide. So then the problem is how we can secure the machine. So first we have to install a concrete path, okay, and then we can put the cage and the gravimeter as shown here, or even we can have a pile to drill down the cage into the ocean bottom, right? So by doing this, then my machine can be installed at the ocean bottom, and then this is about the same case as the installed underground, right? And then by using the technique I developed, we should be able to monitor the gravity change by using one of these design continuously. So next slide. So, but then there is a problem because what if the depth is too deep, or we really don't know how much the mud we expect on the ocean floor, because if it is muddy, then eventually the mud will cover up the machine, which is the problem. So we really have to work hard, and then what kind of design is required, and how we can communicate the machine to the surface and so on. But when injection is made, there will be a platform, right? So on the top of the platform, we can have electricity, and also we can contain liquid helium to maintain the duo really cold, right? So I actually proposed this about a few months ago to Kigam, and then I expect if this is accepted, then we will design a container and put my sensor into the container and install on the ocean surface about 50 meters below. And then when the injection really happens, then we should be able to monitor the migration of CO2 continuously up to 5 to 10 years. So this is very challenging technique. However, if I don't know about Thailand, but if Thailand also has a reservoir offshore, then should be able to adapt this kind of technique. Otherwise, it's difficult to monitor whether the injected CO2 stays there or not. Okay, and the conclusion for this is two. So only superconducting gravimeter has an accuracy and stability to monitor the injected CO2. Plus, if CCM is allowed, then we should focus on the basaltic layer. Okay, in addition to the conventional sedimentary formation, then it's a game changer. Okay, okay, so that's it. Yes.
Thank you very much, Professor Kim, for your presentation. Now it's time for question,
Yep.
comment, or any idea you want to share in this talk, please.
May I share the discussion with you, Dr. Kim? I've been in Calgary a few years ago when they start to use the satellite
Mhm.
to measure the gravity change around the world.
Okay.
Is that a project you're involving in that time in Calgary? It's a long time ago.
Yeah, no, maybe not.
When they're using the orbit of the satellite and then see how the GPS changing to
Yeah.
measure the gravity at that
So
time. Yeah.
did you use Grace satellite or
Yeah,
GOES?
I can't remember but the technique is something that way.
Yeah.
However, it cannot be used in Thailand at that time because the government is not interested in doing that way.
Yes.
I have some comments on that. And why you have only two stations in Korea instead of three? Two is enough to have an accuracy for the GPS, no?
The more the better.
The more the better.
Yeah,
right?
but then the problem is money. It's very
Oh,
expensive.
okay.
It's $0.7 million.
I see.
And also somebody must take care.
Because I'm seeing that if you have two, right? I mean, to measure the distance in to make the best accuracy, it's better to have three locations in Korea, and then you can do
Yes.
yeah, in every direction.
Yes, yeah,
of
you're
earthquake,
very right.
right?
Yeah.
Okay.
The more the better, but
Yes.
then still Korea is a small country.
I see. Okay.
So even though we have many, but they are really
very close.
close. So
Yes.
that's why I ask, for example, Thailand to join the network so that we can extend horizontally our network, which will help
The
great.
second is that how you choose the location of your gravimeter, superconducting.
Oh, for the first one, which was installed a long time ago,
Yeah.
I selected such that the gravimeter is far away from the ocean. So I selected about the center of the South Korea.
So Korea.
And also the Kigam operates a brand new seismological station. So I decided. And for the current machine, I had no choice because Korean government built a underground lab there.
You already have the location.
Yes,
right?
yeah. So I had no option.
There's no limitation for the geological condition.
No.
No.
No,
Okay.
no.
I would like to share on the other subject on CCS.
Okay.
I don't think that Thailand can be a good place for the ideas on the CCS in the basaltic, because in the oceans we don't have any basaltic layer big enough for a good storage. And second is that the basalt in Thailand is just small places, few kilometers square, few kilometers. So it's not good for your ideas on that. But the other thing is that if you would like to do that in the sea between Korea and Japan or Korea with China, I'm not sure whether the maritime law will allow you to do that at this moment. I'm not sure about it, but scientifically, yes, right? But the other dispute on maritime laws maybe prohibit you to do that kinds of tests in the future.
Yeah, it's very important. Even though the location belongs to Korea politically,
I
but
see, yeah.
but that's why we have to monitor how the injected CO2 migrate. So if the injected in Korea
Going
migrate
to
to, for example, the other country, then it's big problem, right?
The idea is good in order to put the carbon to the
Yeah.
basaltic layer, but the way is that the best place
Right.
maybe in Iceland that's okay, but I'm not
Yes.
sure whether the area between Thailand in Thailand, especially in the ocean, and especially in Korea, in the area between Japan and China, or even with North Korea.
Yeah, so the one other thing we need to consider is that Korea also has onshore storage, land storage,
Oh.
but it's difficult to work with people living around. So nobody want
Don't
to
want to have that.
yeah, so it's NIMBY. Therefore, we have to go for the offshore storage. No other option.
The last one is that
Yeah.
we are looking at the big earthquakes to have PEGS, right? Right. You said that you kindly reduce the magnitude down to 6.
That's
So
yeah.
so what is the main criteria to reduce from 8.5 to 6 in
Oh.
order to monitor?
I mean, it's for example, 6, but thing is, my machine is installed in the quietest environment.
Oh.
No noise whatsoever by
Oh.
human being, traffic,
Okay.
or even the migration of water and so
Okay.
on. Very deep. So the quality is excellent. But then still,
The place.
yeah,
Should
the
be,
best place in the world in terms of the distance. And then magnitude, we analyzing it every day to see if
we can. Yeah.
we catch it. And then the horizontal distance, we don't know unless the other country provide the data. That's why we are forming the Asian network, right?
Okay, thank you.
Yeah, thank you.
Is there any question for in the meeting room? So if no, I would like to.
In relation to the CO2 injection to the basaltic layer, may I know what I know? You said that the technology is confirmed. May I know what the issues are? Why it's not internationally accepted?
Oh, you know, that was only tested at Iceland. Okay, so the project name is Calgary. I mean, then the thing is, as I said, it just tested technically, and it worked. But you know, it mineralized too fast, less than 2 years. Then it's really dangerous because the portion of the injection pipe is already you know, it's blocked. Right. So, and also it's about the international law, right? Because conventional CCS is confirmed and allowed, but not on that CCM technology. So there must be a ongoing effort to make that legal, but that's a real challenging technique. So nobody knows what will happen with the technique, but it was confirmed at pilot study in Iceland. So where the mid-oceanic ridge actually goes up to the surface, right? They injected there, and then it was confirmed. It's very, very ultramafic with a good porosity, right? But it's not allowed yet. Not allowed yet. But the ADNOC, ADNOC, it's an Abu Dhabi National Oil Company, and I have a project with ADNOC, and then they are going to test it because you know they near Oman. Okay, there is an ophiolite belt, right? And then they they announce that they will do it soon. So they claim that the ADNOC will be the first commercial oil company to test CCM. So if you Google it, then you can find it. So if they are successful, then they said they will do it because it ophiolite, you know, the ophiolite belt in Persian Gulf, right? So that's what they plan to. Then if it is successful, then it could be commercialized. Then it's a game changer.
Professor, because your title is very technical issue.
Yeah.
It's very a little bit difficult for other people who are not geophysics. So I would like to ask Dr. Titi to conclude in Thai language for our people
Yeah.
that
Yeah.
there might be a better understanding.
Yes, I will provide the full slide to DMR and CCOP.
Okay.
Yeah.
Dr. Titi, please.
ครับที่จริงครับสวัสดีครับ good morning. I just gonna speak Thai to our colleagues so they can understand better what you've been talking about. Just a little bit, just very briefly. ครับก็ที่จริงแล้วช่วยเสริมผมด้วยนะฮะเพราะว่าท่านดร. คิมท่านก็ Professor คิมท่านก็ได้พูดในเรื่องที่น่าสนใจมากนะฮะในเรื่องของการใช้microgravity ในการที่จะ detect ในเรื่องของการทำนายการเกิดแผ่นดินไหวซึ่งในช่วงเวลาช่วงแรกที่สามารถที่จะ detect ได้เนี่ยมันจะต้องมีขนาดแผ่นดินไหวที่มีขนาดใหญ่พอสมควรนะซึ่งในช่วงแรกที่เขาทำก็จะมีขนาดตั้งแต่8 magnitude 8ขึ้นไปแต่ตอนหลังมาแกเคลมว่าสามารถที่จะทำระบบที่สามารถที่จะบอกได้ลงมาถึงที่ประมาณ6 magnitude นะครับซึ่งก็ถือว่าเป็นสิ่งที่ดีเพราะการจริงๆแล้วในประเทศที่เขามีระบบที่เซนซิทีฟกับเรื่องของแผ่นดินไหวเนี่ยอย่างเช่นญี่ปุ่นเขายกตัวอย่างว่าอย่างเช่น1 วินาทีของการที่เรารู้ว่ามันจะเกิดแผ่นดินไหวขนาดใหญ่เนี่ยเขาสามารถที่จะลดความเสียหายได้โดยระบบอย่างเช่นชินคันเซ็นเนี่ยวิ่งเร็วมาก1 วินาทีนี่มีความหมายมากเพราะฉะนั้นถ้าเขาสามารถรู้เนี่ยเตือนปุ๊บแล้วลดความเร็วลงมาเนี่ยจะลดความเสียหายให้ได้เยอะมากอันนี้เป็น1ในตัวอย่างที่แกยกมานะครับในเรื่องงานต่างๆเหล่านี้รายละเอียดทางเทคนิคก็ค่อนข้างเยอะท่านที่ไม่ใช่นักธรณีฟิสิกส์อาจจะมีความรู้สึกว่ามันยากนะมันอะไรแต่ว่าในแง่ของกลุ่มนักวิชาการที่ทำเรื่องแผ่นดินไหวนี่เขาก็คงจะเชี่ยวชาญในเรื่องนี้อยู่ก็น่าจะเข้าใจดีในเรื่องของเทคนิคใหม่ๆตัวนี้ทีนี้ในส่วนหนึ่งที่ท่านได้พูดถึงก็คือในเรื่องของโลเคชันที่ทำเป็นสเตชันขึ้นมาท่านจะเห็นว่ามีการศึกษาโดยตัว Professor Kim เองก็ไปเซตสเตชันประสานงานกับทางรัฐบาลของประเทศเกาหลีเองจัดทำสเตชันขึ้นมาที่ระดับลึกลงไปใต้ผิวดินลงไปเป็นประมาณ1 กิโลนะโดยอาศัยโครงสร้างต่างๆที่มีอยู่แล้วในบริเวณที่มีการทำเหมืองนะทำเหมืองใต้ดินเหมืองเหล็กเหมืองโลหะต่างๆแล้วก็ใช้facility ตรงเนี้ยในการที่จัดตั้งเป็น station ขึ้นมาจากนั้นท่านก็มองดูว่าระบบเนี้ยมันสามารถที่จะมีประสิทธิภาพที่ดีในรัศมีประมาณ500 กิโลเมตรขึ้นไปจนถึงประมาณ 2,000 กิโลเมตรแล้วก็เลยมีการเริ่มจัดตั้งทำ station ต่างๆขึ้นมาให้กระจายไปหลายแห่งทั้งในประเทศเกาหลีญี่ปุ่นแล้วก็ลงมาที่ประเทศจีนไต้หวันซึ่งท่านมองว่าแนวไต้หวันขึ้นไปผ่านเกาหลีถึงญี่ปุ่นเนี่ยมันเป็นแนวที่อยู่ในช่วงรัศมีของประมาณ500 ถึง 1,000 ถึง 2,000 กิโลเมตรซึ่งเป็นรัศมีที่เหมาะสมแต่พอท่านพูดไปเรื่อยๆขยายไปเรื่อยๆเนี่ยท่านก็จะมองว่าโอเคละคราวนี้มาลองประสานทาง CCOP ดูท่านมีแนวคิดว่าอาจจะใช้ CCOP เนี่ยเป็นเบสในการที่จะกระจายขยายสเตชันสำหรับ monitoring ตรงเนี้ยขึ้นมาในบริเวณที่เป็นท่านมองว่าประเทศไทยเนี่ยเป็นจุดที่มีความสำคัญนะน่าที่จะมีสเตชันรวมไปถึงทางอินโดนีเซียแล้วก็ทางเวียดนามนะอันนี้ก็จะเป็นแนวโน้มที่มีโอกาสถ้าหากว่าท่านประสบความสำเร็จในเรื่องของการเจรจากับทาง CCOP ว่าโอเคทำโปรเจกต์พวกนี้นะเราก็อาจจะได้เรียนรู้เทคนิควิธีการพวกนี้เพิ่มขึ้นมาในพื้นที่นะการที่เป็นสเตชันในการ monitoring พวกนี้ไม่ผมว่าไม่เป็นไรครับเพราะว่ามันเป็นเรื่องของการศึกษาวิจัยแล้วก็เป็นการร่วมมือกันทางวิชาการซึ่งอันนี้เองหลายๆประเทศก็จะเห็นว่าทางประเทศบวก3เนี่ย ประเทศเหล่านี้ก็จะมีการจัดตั้งmonitoring station ขึ้นมาเยอะแยะมากมายนะฮะซึ่งเป็นที่เราก็เป็นที่รู้กันอยู่นะครับว่ามีเครือข่ายเหล่านี้อยู่ ถ้าเกิดขึ้นจริงก็จะดี อันนี้ก็คือรวบในส่วนแรกนะครับในส่วนที่สองก็จะท่านก็จะข้ามไปในเรื่องของการcarbon storage ตรงนี้ท่านก็เสนอ แนวคิดที่ดีมากๆนะครับเพราะว่าแล้วก็จะเป็นเทคนิคที่ใหม่นะในเรื่องของการที่เราต้องเข้าใจนิดนึงการกักเก็บคาร์บอนที่เป็นแบบ conventional ก็คือที่ทำกันอยู่ที่รู้จักกันดีก็คือใช้สิ่งที่มีอยู่ในเรื่องของหลุมเจาะปิโตรเลียมต่างๆและกักเก็บคาร์บอนลงไปในชั้นหินโดยเฉพาะชั้นหินทรายโดยปกตินะครับเพราะว่าแหล่งน้ำมันส่วนใหญ่จะอยู่ในหินทรายก็จะกักเก็บลงไปในชั้นหินที่เป็นหินทรายแต่ในขณะเดียวกันท่านก็เสนอในเรื่องของการกักคาร์บอนลงไปในชั้นที่เป็นบาโซลต์หินบาโซลต์ทีนี้ตรงนี้เนี่ย มันต่างกันยังไงการที่กักเก็บลงไปในชั้นหินทรายเนี่ยก็คือเอาคาร์บอนไปเก็บแล้วก็อยู่อย่างนั้นแหละไม่มีการเปลี่ยนแปลงอะไรเป็นเวลาอยู่ได้เป็นหมื่นปีก็ไม่มีการเปลี่ยนแปลงอะไรในขณะที่ท่านเสนอว่าในเรื่องของการกักเก็บลงไปที่ชั้นบาโซลต์เนี่ยคือการอัดคาร์บอนลงไปพร้อมกับน้ำทะเลลงไปด้วยทีนี้ตรงนี้เนี่ยมันจะไปทำให้เกิดปฏิกิริยากับคาร์บอนที่ทำปฏิกิริยากับน้ำที่ไปละลายเอาไอ้ส่วนของแร่ต่างๆที่มันมีอยู่ในนั้นไม่ว่าจะเป็นโอลิวินไพรอกซินอะไรก็แล้วแต่แล้วเกิดเป็นแร่ที่เป็นคาร์บอเนตขึ้นมาในกลุ่มคาร์บอเนตในกลุ่มคาร์บอเนตมันก็จะมีหลายอย่างไล่ไปตั้งแต่แคลไซด์อะไรต่ออะไรนะซึ่งขึ้นอยู่กับตัวอีออนที่มันปล่อยมาในชั้นบาโซลต์ว่ามันจับตัวอะไรกันยังไงเกิดเป็นแร่อะไรได้บ้างนะครับกระบวนการนี้สามารถเกิดขึ้นได้ภายในระยะเวลาไม่เกิน2 ปีและข้อดีของการกักลงไปในชั้นบาโซลต์เนี่ยก็คือไม่จำเป็นจะต้องลึกมากเหมือนกับทางที่กักลงไปในชั้นหินของปิโตรเลียมคือต้องลึกเป็น2-3 กิโลอะไรประมาณนั้นแต่ของบาโซลต์นี่มันลงไปแค่ไม่กี่ร้อยเมตรมันก็สามารถที่จะกักเก็บได้แล้วแต่เผอิญว่าเทคนิคอันนี้มันใหม่มากเพราะฉะนั้นในเรื่องของการยอมรับในเรื่องของในแง่ของตัวบทกฎหมายต่างๆในเรื่องของสิ่งแวดล้อมการไปปรับเปลี่ยนสภาพอะไรต่างๆมันจะเกิดผลกระทบอะไรต่ออะไรนี้อันนี้ยังเป็นเรื่องที่จะต้องถกเถียงต่อสู้กันต่อไปนะครับแต่ฟังดูแล้วก็จะเป็นเทคนิควิธีการที่น่าจะเข้ามามีส่วนสำคัญในกระบวนการ net zero emission ต่างๆของโลกต่อไปในอนาคตนะครับอันนี้ก็หวังว่าถ้าหากว่าทาง Professor Kim ได้มีการเข้ามาดำเนินงานร่วมกับ CCOP ผมว่าในเรื่องนี้ก็น่าจะเกี่ยวข้องได้เหมือนกันเพราะว่าการที่กักเก็บลงไปในบาโซลต์เนี่ยท่านก็บอกแล้วไม่จำเป็นจะต้องเป็นในทะเลบนบกก็ได้นะครับเพราะฉะนั้น on shore on land หรือว่า offshore ก็ได้นะครับตรงนี้ก็ไม่น่าจะน่าจะพอทำได้นะครับท่านในประเทศไทยเพราะว่าเราก็มีชั้นบาโซลต์อยู่พอสมควรทีนี้ในขนาดเท่าไหร่เนี่ยยังอาจจะต้องเป็นประเด็นที่อาจจะต้องพูดคุยกันต่อไปว่าแค่ไหนมันพอถ้ามันเป็นแค่สักกิโลนึงพอนี่มันก็โอเคแต่จะกักแค่ไหนยังไงเพราะตัวนี้ลงไปปุ๊บมันไม่ได้ต้องกักเก็บเอาไว้ว่ามันมีการทำปฏิกิริยาแล้วมันก็จบนะก็คือมันก็เป็นข้อดีอย่างหนึ่งนะครับและเป็นสิ่งที่น่าสนใจมากๆและซึ่งทางเราเองก็นักธรณีของเราก็ค่อนข้างจะใหม่กับเรื่องพวกนี้เพราะเท่าที่ผมทราบอันนี้นอกจากที่ Professor ท่านพูดนิดนึงเท่าที่ผมทราบขณะนี้คือทางปตท.เองเขาก็ทำในเรื่องของคาร์บอนแคปเจอร์ตัวนี้อยู่แต่เขาเป็นเขาเรียกว่า Pilot Project ที่ใช้คาร์บอนจากกระบวนการผลิตของบริษัทลูกของเขาแล้วก็เอาไปลองทดสอบอัดคาร์บอนลงไปเก็บแต่ในลักษณะของการที่ใช้บาโซลต์เนี่ยผมไม่แน่ใจว่าทางปตท.ได้คิดถึงเรื่องนี้หรือยังเพราะว่าอันนี้เป็นเทคโนโลยีที่ค่อนข้างใหม่นะครับก็ในส่วนตรงนี้เพื่อให้มันสั้นก็จะแชร์ประมาณนี้ก่อนนะครับถ้าเกิดใครมีคำถามมีอะไรยังไงก็เรียนเชิญได้ครับมีคำถามบนกระดานครับ
Kim, you have a chat question?
Yes, sure. So I'm going to answer three questions from number three. Okay.
So I think they understand it
Yeah,
more or less.
But thank you
So,
very much.
yeah.
And can I see the CCM slide to answer the last? Can I see the slide, CCM slide? Because the question is about the technology, reference and the cost. I really have no go more and more. Yeah, go more. Okay, right here. Okay, so next slide, please. Next slide. Okay, the cost, I really don't know how much because no one announced, but the project name is CarFix, done in Iceland, and this is the reference. Okay, so please refer to this. It's a very strange name, but it is not the paper, but it is proceeding paper. Okay, so it is published, but I don't know how seriously it was peer reviewed, but it is published in 2016. So please refer to this paper, and it says everything. Okay. And the second question was about the co-seismic gravity change. How big the maximum? That I don't know, but from my machine, the maximum co-seismic change was 2.6 microgal. Okay, that's why it cannot be detected by conventional spring gravimeter. And then sometimes if the gravimeter is very close to the earthquake hypocenter, then the magnitude should be almost unlimited because the gravitational acceleration is inversely proportional to the distance squared, right? And also we have to note that the vertical change of the surface, the height also contribute to the change of the gravity, right? But our case is completely corrected. So the 2.6 microgal, which was the maximum on my machine, is really a accurate number. That was purely created by the mass redistribution. Okay, and then the first question was about the underground gravimeter because it was installed underground. So he or she want to know how we correct for the groundwater, right? It's a very excellent question. Because, as I mentioned, that was built on the base of the current active iron mine. Okay, and then what we found in the middle of the construction of the tunnel was that the side and the below of the tunnel is completely saturated. Maybe because of the mining and the constructing the activity, which means that all the pore spaces are filled with the groundwater. So wherever we actually drill, the groundwater really pumped out. So we really didn't even have to correct for it because we need groundwater correction only when groundwater fluctuate, right? Because of the tide effect, groundwater goes up and down daily. That should be taken into account, but our case is completely saturated. So we didn't have to really correct. And also the ground water aquifer way above the gravimeter, which is near surface, we take into account by using the nearby groundwater data. However, there are not much we can correct it because it's too far. So it's in terms of groundwater, it is good location because not like the other surface location, it is completely saturated. So no change of groundwater level. So we didn't have to correct. So that's my answer to the question number 1. 2 and 3. I think I answered all the questions.
More question? Yes, please.
Excuse me, Professor Kim, may I ask you the question
Sure.
regarding on the monitoring of carbon dioxide in the CCS project
Okay.
on the seafloor. So conventionally now today we use the seismic, right? in
Yeah,
like for
yeah.
example in the Sliner project
Yes.
in Norway. So
Yes, right. Yes.
like 1980 something to
Yes.
nowadays. But
Yeah.
I guess it's the government like try to reduce the cost of the monitoring.
Right.
So
Exactly.
it would be great to use the gravimeter as you mentioned
Yes.
as a sensor on the seafloor. But what I like try to point out and interest is that if you have a small crack or a pre-existing fabric or the fracture above the reservoir that we store the carbon dioxide, would the gravity meter can detect like the changing of the carbon dioxide leakage through the small fault?
That's a good question, and that's the limitation of one gravimeter. So, like a Sleipner, they had many 4D seismic, not many, but few, but it's very expensive. But I must say that seismic is the best way to have a nice snapshot of the plume, right? But then they don't know in between the survey, and it's very expensive, right? So the benefit of the gravimeter is we can continuously monitor, but that the Sleipner case, they only deployed the CG3 gravimeter twice, and they got the difference between 3 years, right? But my proposal is to leave the gravimeter on surface. But as you pointed out, one gravimeter will tell us how much injected CO2 we lose. Okay, so in order to know which direction or where we lose, then we need more than one. Therefore, what I propose is that we need to combine gravimetric monitoring with seismic monitoring so that we can have a complete story. That's a real nice idea, but installing even one gravimeter on the ocean surface is really challenging. If it is, the successful, then in fact, I propose such that we have a multiple platform surrounded by the injection well. So we have an injection well, and for example, we have 4 platforms, and then we migrate the gravimeter sequentially. Then we should be able to identify the direction of the leak or the migration. Otherwise, with the one gravimeter, what we see is only mass change. So, for example, if we inject million ton, but now we ended up with 0.9, then we lost 10% of injected CO2. That's it. But we will have other survey result, right? Seismic.
Right.
Then we should be able to actually interpolate the amount of leak between the time series of the seismic survey. I think that's a real excellent question.
Okay.
Right? Yeah.
Would we have some small questions?
Sure. Yeah.
If we lay out these sensors and then on the area which is quite active, so the sediment is fluctuate from continent and then overlap on the sensor.
Yeah, that's the problem. Yeah.
In terms of communication of the of human and the sensors on the seafloor, is there any problem?
No, I don't think so, because we must have an umbilical code.
Oh,
Because the ocean depth is about only 50 to 70. So there must be a cable
okay.
connected,
Through
but
the
I'm
cable.
I'm concerned about the mud. I'm not talking about losing the machine, but the mud is a real thick mass. So then the gravity will be changed by the accumulation of the mud. That should be taken care of. That's challenging. But I never know until we install something on the bottom of the ocean and see how it works. Yeah.
Yes, please.
Okay, thank you. Thank you, Professor Kim, for your presentation. It's very interesting. I just have 2 quick questions. So first one, I noticed that your the equipment, the superconductive, I mean the effective range for accurate detection It's so radius it's 2,000 kilometer, right?
Between detect earthquake, right?
Yeah, detect
Between 1 and 2,000.
2,000.
Between.
So I noticed that you covered most part of Japan and some part of China. So I do believe that you already detected the earthquake that happened in Japan this year, early this year, right? It's quite a huge one. So my question is now for your equipment, I mean for your equipment is located in Korea, South Korea. So is there an effective way, I mean mechanism to own the other country? So after you detect the earthquake, maybe 100 or 150 seconds in advance. So is there a way to own other country?
Yeah, that's why I want to make a network. That's why, because the single machine has the limitation of the distance, right? If we have a network,
Yeah.
then the range will be extended seriously. But the problem is we have to share the data and we have to analyze real time, right? But that's not easy to be shared because it's government data normally. I believe the seismic network data belongs to Thailand government. So I'm not sure whether the Thailand government is willing to share the data to other countries. And then I know what you mean, because still my machine, my instrument did not detect PEGS. It detects the earthquake like other seismometers do, right? So to be clear, didn't detect any PEGS yet. So I don't know, the between which distance or minimum what magnitude my machine can detect the speed of light gravity. Not yet happen. Not yet happen.
Yeah, because also end of last year there was a earthquake happened in China, but I saw the location is out of your
Too far.
Yeah, it's too far.
Yeah.
So
And Japan only, and then it was too small. Yeah, that's the problem. So, but we are working until we conclude.
So ideally, so just in a scientific way, every 4,000 kilometer. So if we can set up equipment every
Theoretically, yes.
4,000.
Theoretically, then we
So
can
that is
cover
the coverable
entire
area.
Exactly, yeah.
Oh, I see.
But Yemi was kind of lucky to locate that distance between all the potential future earthquake epicenter. It's very lucky, right?
But it didn't cover the Indonesia, which is also an active
Right.
area.
Yeah, but the Korea doesn't believe that they expect any damage by Indonesian earthquake other than tsunami.
No.
Right? So Japan is our imminent risk, right? Japan or Taiwan. Our means Korea's problem, right? So that's why the Sumatra, I don't know how far the Sumatra is from Thailand. And also Thailand is lucky because it is surrounded by other landmass, right? So I really have to check the distance, and then that's why I suggest to share the data through the CCOP with other countries, so that may be possible to detect the gravity signal.
Thank you.
Yeah.
And my second question is related to the CCM, the carbon captured by the mafic rocks. So I wonder, so what is the biggest challenge now for commercialize this activity, or no, so to commercialize this technology?
Okay, so the reason why I added the CCM slide is because I worked briefly for Korean National Oil Company about the location of the basaltic layer, and also I have experience work with ADNOC, Abu Dhabi company, which intend to do it. So, I mean, I don't think it's expensive. I mean, in terms of money, I don't think it's expensive because we don't have to we don't have to make it supercritical. All we need is to mix the CO2 with the seawater. It's everywhere, right? And then just put it, and then, the more the mafic the rock is, the faster the mineralization will happen. So at there, right? Then it takes 2 years. That's the challenge, I think. So they have to inject quickly, then seal it. Then it should be okay, but you never know what will happen. Maybe it expands and the break the pipe. It could be disaster. We never know. So it is really a challenging but promising technique, and the people even do not know what will happen, to be honest. But I don't know, maybe it's a law. Everything is about the regulation, protocol, and law.
So rapid mineralization could decrease the porosity
Dramatically.
dramatically.
That's the problem. So it may rupture the rock, right? It may break the facility. So it's not going to be easy to be allowed, I think. It's not going to be easy.
Because I remember I saw some news or research. They just to mine the basalt and grind into a small particle and to spray into grassland or cropland to capture, to add maybe as an alternative. They don't need to inject. They don't need to use a pipe. They don't need to use a tunnel. They just spray the basaltic maybe ground to the farmland as the alternative. That could be, but I don't know whether or not it could be alternative for this one. So if the mineralization, the rapid mineralization could be the biggest challenge for this technique. I don't know.
I think so. So it is an advantage, but it is also disadvantage, right?
Oh.
So until we figure out that this CCM is 100% safe, then it will not be commercialized. So just let's pay attention to what ADNOC does, because they announced that they will test it and the ultramafic ophiolite, and then I don't know really. But this is a challenging but promising technique to dramatically expand the capacity.
Okay, thank you.
Yeah.
There are 3 questions from Professor Dr. Panya. The first one is location of machine installment must be in the very low size seismicity area. And the second one is minimum time is the 1 second before the earthquake. How about the maximum time? And the last one is not many areas are expected for the next big earthquake.
Okay, the first question, the gravity acceleration requires distance. Okay, so that's why there is a distance limitation, 1 to 2,000, because it needs to be saturated, even though the signal travels at the speed of light. So, and then I'm not sure if I understand correctly, but if you want to monitor the elastic seismic signal, it is much better when sensor is closer to the source. So that's why there are so many seismometer network in Japan, but none of them actually can detect the gravity signal because it's too close. Because can you open the first slide? Almost first slide. The first figure, I would say. You have to go the almost first slide of the present. Few more, please. More. Yeah, one more. Yeah, this is it because as you see in this figure, okay, so this is the hypocenter of your space, and then there are two sources of PEGS. One is direct disturbance traveling through the air, and then this space vibrate or disturb the nearby area. So there is a gravity change which actually induce another signal. That's why it requires the distance, even though it travels at the speed of light. So there is a limitation, but we think it will be overcome if we have a network of data vertically and horizontally. And then the second question, I am not sure if I understood correctly, but the 1 second means, I think it's a sampling thing, and I don't know what the maximum he meant, but my machine is set up with a sampling rate of 1 second, and that's it. And then it can be changed, it can be adjusted. And then for the earthquake study, we do not need a very high frequency data. Okay? And then the last question I really couldn't understand. If somebody can.
The last question is not many areas are expected for the next big earthquake. Not many areas are expected for the next big earthquake.
So
May I
Sure.
clarify the question is that we do not expect a big earthquake in the world, right?
Yeah. Of course, it depends on the.
That's right. So his question is that because we cannot expect a big earthquake in the world, in the earth, in our earth. It means that you have less chance to get more informations about your machine.
Yes. But then the Korean site is excellent because it is almost, surrounded by potential. Yeah. Yes. Yeah.
If no any question, thank you very much for every question and idea sharing in this special talk. And to remarks this special occasion, I would like to invite Mr. Thinakon Thatong, the inspector, to give a token of appreciation to Professor Dr. Kim. Yeah, just in the front of, Professor, please. And after that, we have a group photo. Yeah. The group photo, please. Everyone are invited to take a picture.
can leave to